Hey guys, so today I want to talk about the book The Law of Thermodynamics by Peter Atkins. Very short introduction. This is an introduction to his book on the 4 laws that drive the universe. As you can tell, it's a book on thermodynamics. Not the most interesting topic in the world, unless you're really into it or a physicist. I personally studied this when I was doing my degree in mechanical engineering, and I found it so hard, so tough. I'm not sure it was taught in the correct way when I was doing it, and I just could not get my head around it at all. I think I resat it 3 times, which I am definitely not proud of, to say the least. It always really frustrated me. I just could not get the hang of it. The concepts, it was just a mess, really. But a couple of years later, this year, I found I was in Waterstones and they were selling this book for $5, and I had a quick look through, and it was under 100 pages. I mean, it's very nicely written, very concise, and I thought, oh, what the hell, I'll give it a go. So, read it. It's under 100 pages, and I was blown away with it. Just, quite frankly, just blown aback. What took me a year to understand in terms of the fundamentals, it's taught me in 2 days. Or you could probably read it in a day. I'm a really slow reader. It's under 100 pages, 4 chapters, based on the 4 laws of thermodynamics: the 0th law, 1st law, 2nd law, and 3rd law. Confusing order, I know, but it's all explained in the book. I mean, the diagrams are very concise, they're very simple, easy to understand. He writes every term and every state and name is explained within a sentence, so you get a quick, concise look at it, understanding. It doesn't fluff about like most other books. I mean, it's really short, precise, straight to the point. You're not having to read 300 pages to get 100 pages worth of knowledge. Really blown back by this book. I think I might actually invest in buying this. The 4 laws that drive the universe. Because the only thing it doesn't have in here are things like diesel engine cycles, refrigeration cycles, all the experiments and stuff that we use today that was explained. Those were the things we mainly focused on in my course. But I reckon if this guy writes the way he does, it's definitely worth a read. Right, so getting straight into it, the 1st law, as he puts in this, after a brief introduction, explain what thermodynamics is the 0th law. Confusing, I know. The reason it's called the 0th law was because it should originally be at the start, but it didn't become a law and wasn't recognized as one until after the 1st and 2nd laws were already established. So the 0th law, in summary, the 0th law relates to temperature, the 1st law relates to energy, 2nd law, give me a second, I should know this because I just read the book, is entropy, and the 3rd law, unprofessional, the unattainability of 0. So, true 0 degrees. So a bit odd. The 3rd law isn't a law that correlates the understanding of the 1st, 2nd, and 0th law like the other 3 do. A bit weird, I know, but you gotta bear with me on this one. So the 0th law is all about temperature. So if you take the world around us, everything we do, everything you see, and imagine a baby just coming into this world, absolutely 0 understanding of what's going around it. How do you start contemplating, understanding how things are and what they are and how everything is? You do that by finding units of measurement. Now, if you think to begin, in this day and age, we have units and scales for everything under the sun, but if you think about those units of measurement, how did we come to get them in the first place? How did we achieve centimeters, meters, degrees, centigrade, degrees Fahrenheit, units of measurement, usually like liters, kilograms, weights, volumes, anything. Well, it all in terms of the laws of thermodynamics, all started with temperature. So that is, every single item and object has a temperature. So if you take room, for instance, room temperature, temperature of this book, temperature of myself, inner core temperature of a human, all has a temperature. So how do we start correlating them? How do we start making a comparison or a scale? So to begin with, a temperature, how do we know that two things that are, let's say, two cities apart are the same temperature? Well, if you take an object, say this book, and you're able to transport this book from this city to another city, so city A to city B. This is item C. So let's say item A in city A is another book, exactly same dimensions, parameters, exactly the same as this book, and you put them together, and you find out that item A equals item C. So this book, item C, is the same temperature as the first book in city A. And you take item C and you go along and you take it to city B, where there's another book that's same size, same dimension, everything about it's the same. You put them together and you find out they're both the same temperature. This could be by hand touch, this could be by the scale. At this point in the basis, we don't have a scale, so let's say by touch, you're like, oh, they're the same. So by that breakdown, that equation is, if A equals C and B equals C, then A must equal B. So there we go, we've got our first equation, our first length of scale. So if this book or anything here wasn't the same, then it would disprove parts of the equation, which would mean that certain thing, you could equate what does and what doesn't have the same temperature. Very rudimentary, I know, to begin with, but you gotta bear in mind this is going from a concept of not knowing anything at all and then building up to the knowledge we have today. Right, so next is the first law. So the second thing we're going to talk about is the first law. It's a bit weird that the second law is called the first law, but you get the picture. So this second law is about energy, the concept of work. So if we go from the zeroth law, this is why the zeroth law was important to go first. So we now know, we don't necessarily know what temperature is. We just know that some things feel different temperatures to others. So we've got our first unit of comparison. So some things are warmer than, feel hotter than others, some feel colder. All we know is that hotter things feel different from colder things. And we have our first basis of comparison equation. So if A equals B and B equals C, then A equals B. If any of them aren't true, then they don't equal each other. Very rudimentary, but that's what we've got. So the first law is about energy. So how do we define temperature? How do we know what temperature is? So with energy, we utilize the process of energy called work. Now that's how much effort, how much force, how much generally effort you put into something. So what they found was the hotter something was, the bigger, higher the temperature, the quicker the atoms collided with each other. Just random collisions occurred on a quicker basis. And vice versa. When it got colder, the energy got colder. Sorry, the energy slowed, the work slowed down and the atoms collided less. Now this is only a quick rundown of what's in this. There's a set of experiments they quickly go through in a set of different systems to equate this. But in general, the quicker the atoms move, the higher the temperature. The slower the atoms move, the less they collide, the cooler it is. Now, through this, we know hotter things are hot, colder things are cold. But what if we put two things side by side? Eventually, they become the same temperature, or there's a transfer of energy. So what they found was, if you take a hot object, let's say 21 degrees Celsius, you take a cold object, let's say 11 degrees Celsius, and you put them together, say this is the exact same dimensions and parameters of this book, for example, and it's in an isolated system, let's say some sort of vacuum. You put them together, eventually what will happen is, so the atoms in here are colliding quicker than are colliding in here. So when you put them together, the intersection between the two, these atoms start colliding with these atoms here. And the more they collide, the more they start to collide with other parts, the other atoms that aren't moving as quickly. So what you find over time is a lot of the energy here gets transferred via work over to here, speeding these atoms up, but at the same time, because of the effort it took to speed these atoms up, the atoms here slowed down. Eventually what you'd find, if you gave it an infinite amount of time, that these two would eventually become the same temperature. So and it would happen, this would decrease and this would increase until they became the same. So if you take it by the basis of them being the exact same parameter and no external forces factors affecting it, there's originally a 10-degree difference. So by splitting it in half, this would decrease by 5 degrees and this would increase by 5 degrees. So this would go from 21 degrees Celsius to 16 degrees Celsius, and this would go from 11 degrees Celsius to 16 degrees Celsius, and they would match. So that effort of work allows us to start understanding what temperature is. It's the amount of collisions of the atoms. Now with this, you can start developing a scale. So pick a unit where atoms are colliding at a certain amount of times, maybe per second, maybe per minute. Obviously you can't do that under a microscope, it's impossible. This is theoretical, it proved by a set of experiments, but you choose a set of movements by an atom and you would give that a number or a letter, or a lot of the times something from the Greek alphabet. So for instance, for this we'll take water. So this is how degrees Celsius came about. You take the freezing point of water and the boiling point of water. So the point where liquid becomes a solid and the point where liquid becomes a vapor or a gas. Those are our two parameters. So we'll give one 0 and one 100. So the work of the atoms as water is freezing, and the work of the atoms as it boils and turns to vapor. That's our defined scale, 0 to 100. And then all you have to do after that point is set an equal amount of divisions for all numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 70, 71, 72, 73, all the way to 100. And there you've got your scale. And then because you know the unit of that division, you can then go beyond that scale. You can go -1, -2, -3, 101, 102, 103, and just keep going like that. Now, the issue is with all of this is there is also what's known as absolute zero. So that's the coldest temperature can be at all. So it gets to the point where atoms no longer collide or vibrate. They just become perfectly still. Now that becomes our point 0. Our, in this case, minus 273 degrees centigrade. Now, how they did that was, obviously, that becomes quite difficult to use in terms of thermodynamics, dealing with all these theoretical numbers on an arbitrary scale that we as humans came up with. So they decided we'll take absolute zero and we'll make a scale, and this would be the thermodynamic scale that's based off degrees centigrade, but we'll call it Kelvin. There's no degrees, just Kelvin. And essentially it all worked out where it was found that if you take the unit points, or the scale of centigrade for Kelvin, that degrees centigrade is 273, so the 273 degrees warmer than 0 Kelvin. So 0 degrees centigrade is 273 degrees more than degrees Kelvin. There's also a point, I think it's 1.5, can go on for ages, but we'll leave it at 273. So minus 273 degrees Celsius is absolute zero, 0 Kelvin. And if you work your way up from there, you can then find your basis. Obviously, the reason we still use degrees Celsius is trying to use for everyday use. So, for instance, inside a house, usually 21 to 23 degrees Celsius. You can't say 295.15, it gets really messy. So that's the main reason we still keep things like Fahrenheit and Celsius in today's life, for ease of use, really. So the third law is, well, third is the second law. This is all to do with the release of entropy. Now, what they found doing all these experiments was no system was completely 100% efficient. It just did not occur in reality. On paper, worked fine. In reality, never occurs. And the reason for that is what's called entropy, which is almost described as a tax for doing work. So for instance, atoms moving quicker heats the system up. You, as a person, start running, you start expelling loads of energy as heat, exhaustion, sweat, just all the tax that comes from physical movement and existing, really. So what they found was, and they named this entropy. So entropy is the tax for existing and doing things. So you've got, let's say, a system, a heat, diesel combustion, internal combustion engine for your car. Is that 100% efficient? Absolutely not. If you think about it, you've got your heat transfer throughout the mechanism as your fuel load combusts. As it goes through the system, you've got that transfer of work for movement. You've got the factors of friction as you rotate and turn. And generally, that's what it is. It's quite confusing to actually explain without having diagrams and stuff to show you. But essentially, entropy is a force of tax for doing work. So lastly is the third law of thermodynamics, or the fourth, which is the fourth law, but it's called the third law. This is the last one, I promise. Now the third law isn't so much of a law as when compared to the previous three laws. It's more of an expression or a fact. It doesn't correlate so much into understanding the first three. Now the third law is the unattainability of absolute zero. How on paper it's fine, very easy to do. In the real world, it is at this point impossible to reach 0 Kelvin. So absolute zero. They've come very close. There's people who've dedicated their lives to trying to get as close to absolute zero as they can, and have done extremely well. But at this point, it's been unattainable. Nobody has even have been close, but have yet to achieve it. My theory, personally, on this is that 0 Kelvin requires an atom to stand absolutely still, just zero movements. But if you think about on Earth, we've got solar rays coming down and all the time, and where would we physically put an atom that wouldn't even have an air source around it, where it's not even absorbing any sort of radiation, any rays, anything that more or less keeps us alive on this planet? You'd have to go into space to do that. But how do you get an atom into space? How do you keep measuring that atom while it's in space? And how far away do you have to go before the solar rays no longer touch it? That's my theory, at least. Could be wrong, could be speaking garbage, but that's how I interpreted it. So in the real world, you can put it in all kinds of systems, all kind of vacuums, but at the end of the day, the objects that are in the vacuums, anything you use to physically measure the atom, will cause a state, because they're not at absolute zero to begin with, they will radiate some work that will cause that atom to eventually put in work. So that is my theory on why you can't get it to absolute zero. There is probably online a better expression for this, a better term, but the final law is the unattainability of absolute zero. And that more or less sums up the whole book. That's what it talks about. You got zeroth law, first law, second law, third law. Zeroth law is based on finding temperature. Second law is based on energy and work. First law is on that. Second law is on entropy and finding entropy, and final law, the third law, is on the unattainability of zero. I mean, even if you're not into physics, or if you are into physics, great, it's a book you should get. I mean, if you're not and you're just curious and you want to understand a little bit more of the world around you, I would highly recommend it. If you're studying physics or engineering or really any sort of technical subject, it helps with your course, helps a bit of your understanding, helps you understand the world around you. And yeah, it's a fantastic book, and for £5 you can't go wrong. There's a set of these books actually for different models, and I might try and pick another one or two up. I really enjoyed this actually. It was a good little learner. So pick yourself up the laws of thermodynamics and get a little bit smarter.